Okay, let's continue the lesson. Okay, so I would like to talk more about linear space, especially using a very special way, which is activation function visualization. Okay, this article is provided by some some researchers. However, this is written in Chinese, so I will explain it in the class. Okay, so here is the activation function visualization. Okay, so let's go back to here. Okay, so here is some example. I want to do some demonstration. Okay, so basically when we talk about activation function, actually it has even more very important. It plays a very important role when we design neural network. Okay, they are not just nonlinear relation. Describe the nonlinear relationship between input data and the output target. Okay, so basically, let's see. Okay, so of course there are several different activation function. Okay, you can see that for example there are some function right here. So here is the for example that is the x, or that is ax plus b. Okay, something like the result. Okay, we will pass through the result to the activation function before you output the value to the next layer, right? So there are several different layers. There's several different activation right here, and most of them they are we call they are smooth functions。中文就称之为它是一个平滑的曲线。它的平滑曲线。那平滑的原因是因为它要在任意的点上都可以做微分。所以你可以知道它的设计基本上是这样子。The reason why we wish the activation function is smooth, that is because it can be differentiated at any point. Okay, so that after we apply those function, those activation function can be can do partial differentiation. Okay, so that is the reason why they are smooth functions. Okay, after we do, if we apply partial differentiation on those activation function, we can see that this is the gradient at each point after we apply different activation function. 好，中文的意思就是说，如果我们把刚刚那些数值比如说 x 加 b 把它 apply 到activation function 之后然后我们不是要对那个 x 做偏微分嘛？那偏微分的时候，那个 gradient 就会长像这个样子。就是导数了我们以中文的讲，这是导数了And as we can see that this one is sigmoid. This one. Because the sigmoid function is right here, right? It's right here. Because the output of sigmoid function would be very smooth, very the gradient does not change very dramatically. 中文的翻译是说，你看那个 sigmoid 这个 function， 因为它的那个范围是正1到0之间嘛，然后它很平缓，对不对？所以它的微分呢，就是它的切线方向它的值也蛮缓的。它的切分对不起，它的微分最剧烈的值是在那个输入值是0的时候嘛，那个地方斜率最大嘛。可是那斜率是多少？那斜率才0.2多而已。就是下面这张图上有写在这里So you can see that the gradient of the sigmoid function, the value is quite low. Okay, the value is quite low. That means when we do partial differentiation, okay, we would like to minimize the value, right? And there are some weight, okay, after we do partial differentiation, okay? So if the value is quite small, which means the weight is the gradient, okay, it's very small. 好，中文的意思是说，当我们在做偏微分的时候那我们不是会微分最找它最小值的那个 loss function 嘛？在偏微分的过程当中，因为那个值是乘上去的嘛，也就是说它会乘上一些比较小的值。 因为它是微分过的嘛，我们要去明买这个值嘛，所以会导致说我们在 passing 这个值过去的时候，常常会遇到一个问题，就是这个问题叫做中文翻译成梯度消失的问题哈，梯度消失。好，那梯度消失的问题就是说呢，你在因为通常neural network有很多层嘛，对不对？那每一层都会有一个微分嘛，然后就一直乘，那它会越乘越小，越乘越小。那也就是说呢 ，information 呢一直往后递延的时候，其实最后的 information 就不见了，因为值越来越小嘛。好，值越来越小 ，OK， 那就很麻烦 ，OK。So that is so we can say that the slope of the sigmoid 就是 sigmoid 的斜率啊。It's very small. The largest one is that is 0.5. Okay, so when you do partial differentiation, when you do backpropagation, okay, the times a lot of different weights, right? And their partial differentiation values. So the information passed from the left hand side to the right hand side. If you have many layers, and many layers they have for each layer they have activation function, and then you use sigmoid function, it usually encounter a problem which is called gradient valanche problem, which means the information will be lost in such kind of deep neural network because we have different many layers, and each layers will have a very small gradient to pass the information from left hand side to the right hand side. Okay, so sometimes we use another version of functions called hyperbolic tangent, because hyperbolic tangent its gradient is from 0 to 1, right? And at the 0 point right here, if your input is 0 and your output will be very close to so that means hyperbolic tangent h. Now for example your input exists, that will be very close to your input will be very close to your output if you use a hyperbolic tangent as your activation function. So you can keep the information, the message from the left hand side and pass it to the right hand side if you really want to keep the value. Okay, so that is different gradient of activation function. Okay, so let's take a look at some other activation function which is not that smooth. Okay, so that is ReLU, right? ReLU looks like this. It has a turning point, and a very sharp turning point, so it is not differentiable at the original point. 就是 ReLU 这一类型的 activation function 啊，它们都有一个转折点哈。那这个转折点就会导致它是不可导的嘛，哈，这个高中大家都学过嘛，哈。可是因为它不可导的点只有那个点而已，所以实际上我们在做这个微分的时候，我们还是可以特别的针对那个点去讨论说，在那个点上的微分可能会是怎么样子的，或者把值带进去算就好了嘛，哈。但是没有关系 ，so 这就是有一个这样子还蛮简单的转折点，所以对偏微分来说应该是没有什么问题的哈。那当然有人觉得说这个还要特别去讨论那个点就很麻烦了哈，所以就有其他不同的跟 ReLU 长得很像的变体。So of course, if you don't want to do if you want your activation function is very smooth, can be differentiated at any point. So there are several different versions. Okay, for example, that is called soft plus. Okay, at the origin point, it is differentiable. Okay, some other variation. Okay, there's some other variation right here. Okay, you can choose either one of them if you want to make your activation function to be very smooth. Okay, so when you there's a tip right here. Okay, if you use ReLU as your activation function, Okay, and of course you have to apply an optimizer, right? And this optimizer, you should set a learning rate. Yeah. So most of the time, okay, it is just it's just a tip. Okay, most of the time, do not use large learning rate. If you use ReLU as your activation function, most of the time we will not use a large learning rate. Okay, it will cause a problem. Okay, it will cause a problem because half of the data, right? Half of the data, the input is, for example, x plus b is right here. Half of the data, if the value of x plus b is less than arrow, then the ReLU will output 0, which means it will not pass the information of x to the right hand side, right? So it caused a problem called dead neuron. It caused dead neuron because half of the data will become 0 after pass through the ReLU activation function. So when you do partial differentiation, or when you pass the data from left hand side to right hand side, this neuron will not be activated, right? So we don't use a large learning rate, because when you use a large learning rate, okay, the data will try to optimize its loss function, right? And it will search a larger area, right? Because you have a larger learning rate, so you can, for each step, you close to the lowest loss function. Okay, it will search a larger area. It would be much easier for you to touch some point which this weight will, after they pass through the ReLU, the output rate will be close to will be 0. So that means the neuron dies. Okay, so that is just a tip. Okay, we don't discuss the actual mathematical theory behind it, but that's just a recommendation. Okay, so that is okay. So let's go to the next one. Okay, so that is the gradient of different ReLU-like activation function. Okay, so you can see that for soft plus ELU or some other thing, I think soft plus is much better than ReLU, because it can be differentiated at each point. Okay, at each point. Okay, so that is okay. So let's go back to next one. I think that's very important. So let's take some time to take this example. So if we have some data like this, okay, x1 and x2, okay, so you simply just put some random point in your original space. Okay, so let's assume it is a circle like this. Okay, it's a circle like this. So after we apply sigmoid, okay, after we apply sigmoid, so we have after we apply sigmoid, we can see that for example, we can use this. We can use the okay, we draw another figure. Okay. For example, there is a data point right here, right? Point P. Okay, so its value is xy, x1, x2 in the original space. Okay, after they apply sigmoid function, hyperbolic tangent function, ReLU function, ELU function, and some other activation function. Okay, as we mentioned before, okay, for ReLU, all the information which is less than 0 will be represented as 0. after you pass through ReLU function. So the information less than 0 will disappear. All the data point, no matter, so for example right here, rather in this way, which is maybe better. Okay. For example, we have data point right here. We have the space right here. Okay. So data point P. Okay. Data point P. We use ReLU as an example, which is more easier for you to understand. Okay. The data point P, after they pass through ReLU activation function, okay, you can see that if there is a data point right here, right, called A, because its value, its x1 value is less than 0. So that after you pass through the activation function, the data will be squeezed to here. Right, because the output value of x1, so that should be ReLU x1, right? So value becomes 0 because, for example, originally it could be +1 and minus +1, for example. A originally in the original space it is +1 and -1 is coordinate, but after you pass through ReLU, okay, it becomes 0 and the ReLU +1. It is A's new coordinate after it passed through ReLU. So basically, when we do activation function, okay, depend on different activation function you use right here, you squeeze the data from the original space to a new latent space. You squeeze the data, right? That is an example of if you use activation function, which is ReLU, you squeeze the data, right? You squeeze the data. Okay, so there are different types of ways to squeeze data. Okay, sigmoid. Okay, they squeeze the data. They will ignore the data at which is very large. They squeeze those data point at which is far away from the original point. They squeeze it to, and you can see that sigmoid is right here, right? It's right here. If your data is very, very far away somewhere here, it will be squeezed to somewhere very close to 0. If your data is very, very small, far away from original data point, the data will be squeezed to 0. So basically, if we pay attention to this one, right? For P, or for some data points, it's right here, F, right? It is a little bit far away from the original data point, right? So it will squeeze back to 1, right? So if there is a data point right here, F2, right? It is minus. It is in the both of the x1 and s2 value, they are minus value, they are negative value, and they are very far away from 0, right? They will squeeze back to 0. So basically, I think it's somewhere right here, F2, 0, 0, right? 0, 0. I think we should draw it in this way. Originally, F2 is very far away from 0 point, and they are negative numbers, right? But after pass through sigmoid function, they will both squeeze to 0, 0. That is why we that is because we apply sigmoid function. So basically, if we visualize those activation function, they are somehow tell us how do we squeeze the original data distribution from the original space. Okay, of course, they are only 2-dimensional. You can use a very high dimension data, and then squeeze the data into a specific area, right? And as we can see, for example, for the hyperbolic tangent, right? For hyperbolic tangent, okay, data which is far away from the original data point will be squeezed to here, but data which is very close to original data point will stay in the original place, right? That is because it's, as we mentioned before, okay, that is because the gradient of hyperbolic tangent has such kind of features, has such kind of property. Okay, you're very close to 0, your data point, your input and your output will be very, very similar, which means in this figure, it's right here. If you were very close to 0, your original input and your output will be very close. But if you are very far away from 0, and you will be squeezed to certain area, which is at the edge of this figure. Okay, there are several different types of so that is, so we have different, so please take some time to take a look at these figures. Okay, if you don't do any activation function, your input and output will be the same. If you do sigmoid function, the data at the negative side will be squeezed to the 0 point, right? For a tangent activation function, the data which is very close to 0 will maintain its value, and on the other way, if your input value is very far away from the 0, far away from the original point, it will be squeezed to somewhere. Okay, for ReLU, negative value will be ignored, and positive value will be mapped to some place. I use ELU, and some other things. Okay, and for the first row, okay, for the first row, that is, and okay, we use several. N equals to 2. That means we do 2 times of activation function. So that means the original input is x. We pass the original x to activation function, for example, sigmoid, twice. Okay, and that is, we squeeze the data 5 times. We squeeze the data 30 times, and by using different activation functions. So as you can see that those data will be squeezed to a very strange shape or a distribution in the new London space. Okay, so that is how do you squeeze data, and sometimes you can for different activations, sometimes you can rotate the data, right? Sometimes you can scratch, you can pull the data, push the data to a new shape by using activation function. Okay, so let's go back to here. Usually we will say that, okay, a neural network may we can say which one is to. Usually when we formulate a neural network, that could be something like the activation function plus wx plus b, and then right, and again, this is the first layer, right? Again, we use this as the input and pass it through to the second layer. So maybe we should use 1 right here, right? We pass it through to a second layer, and we have a second layer, and we pass it to the second activation function, and then the result is y. Sometimes we can use a very simple mathematic representation to represent, for example, that is a two-layer neural network, right? Okay, so basically, the A right here, the activation function we used right here, they try to squeeze, push the data, the input data, and put it in we say map, or we say transform the data to a new linear space. Okay, so that is push the data. Okay, and then the weights right here, and the B right here. Okay, those parameters that help us to rotate the data or do some linear transformation. Okay, as we can, I think we have talked about this concept before. Okay, if you have a data which is original, this one is right here, and then you apply a polynomial transformation 就是你做一个那个多项式的运算的时候 ，actually it maps to rotation。就是说你做这个多项式的运算的时候，实际上你就把它想成嘛，因为我们以前高中都有教过嘛，我们可以把它想成说它是一个对一个向量的角度西塔的向逆时针旋转那个西塔的角度嘛。我们高中应该有学过嘛。逆时针旋转西塔角的时候，就乘以 sin、cosine 跟 cosine 负 sin 的那个 x 值跟 x1 值跟 x2 的值嘛。所以你可以把它想成说 polynomial 的计算，实际上就是一种数据的 remapping， 就是它从原空间把它 map 到另外的空间。那大部分的想法应该就是一样是拉伸、旋转，然后跟平移。因为我们还有 b 嘛 ，b 是平移嘛，大家记得吗？就是好，所以实际上 neural network 如果你不要以 neural network 的形式讲说它在 pass information 从左边到右边的话，你可以把它想成说这些公式里面的那个 W 实际上是带原资料做旋转跟平移，然后那个打 A 的功能那根据我们刚刚上面看的那个例子嘛，它在做资料的旋转缩放也算缩放跟拉伸，还有最重要的是折叠，可以吗？好，因为你把东西变成正变成负的，它就翻过来嘛，那就有点像折纸一样变成折叠了所以实际上我们的 neural network， 所以我们一般都是画右边这个图嘛，对不对 ？pass information 从 x、y， 然后到 h1， 然后到 y prime、x prime， 然后到 p1、p2 做 softmax， 它好像是一个纯数学的运算，把资料从左移到右边，然后再乘上一个 weight， 然后 weight 再做外面再做 activation function 做一个非线性的关系的转换，听起来好像很玄幻，但实际上以纯数学的空间角度的例子来说的话，它实际上就是在描述原资料怎么样经过一连串的旋转、缩放、拉推、折叠、平移这些东西，然后使至于原空间可以被折叠成另外一个样子，那个样子我们等一下会看。好，我要用英文再讲一遍哈。So basically, when we talk about neural network, we usually use this figure, right? This figure. How do we pass the information from left-hand side, pass through different neurons, and neuron will have different weights to receive the information from left-hand side and pass it to the activation function to do some nonlinear relationship, nonlinear mapping to the right-hand side, and so on and so forth. We have different layers to do such kind of things. But however, if you use a visualized way to describe this data, okay, it can be described as this way. And as we can see, those weights, those intercept, and those activation function, they can view as the original data in the original space, and after they pass through a layer, they will do such kind of rotation, zoom in, zoom out scale, to do some kind of shift. Okay, so the original space will be mapped to a new latent space, and new latent space will have, of course, they have the original data is right here, but the shape of the original data is a little bit different. And after they pass through different layers, so they have different type of rotations, scale up, shift, rotation, whatever, or different kind of things. They will map to a new space. And we do use the last new space to help us to do prediction or to do classification. So take a look at the following figure. I think that's very, very important. Okay, we can see that. For example, if we have a very simple neural network like this one, okay, X, Y, and 4 hidden neurons, and X, Y, prime Y, and we have a softmax. Okay, so if we apply ReLU right here, okay, so the step right here is how many partial differentiation, how many data we like to tune this neural network. But visually, it means how many times we can squeeze, rotate, or change our latent space. So that is, okay, for the first time, if we use our training data, right, we have a new weight, right, and we use this new weight to map the original data to a new Y. So that is the, if you only do such kind of training once, okay, the data will be like this. The original data is like this. It's a circle. It's two circles, okay, with a red data point and purple data point. If you only train those data once, the weight you trained will be like this. And after you train 50 times, that means you can fold, you can rotate, you can do a lot of things. Okay, the shape is a little bit different, right? And our target is to differentiate the red data point and the purple data point. So you can see that with different trainings, and we have better weights. Those better weights can mix those function value to be lower for each time we train the data. So after 400 times we train this data, okay, as we can see that the original data distribution will be gradually changed by the current neural network. Okay, so basically, because the idea is we like to the Y right here. Okay, the Y right here we like to distinguish red points and the purple point. So your neural network, your weight will help us to transform the original data, so that we can easily partition red data and purple data. So there are several different rotations, folding, and something like that. So that after that, we can have a very nice new latent space, and this new latent space can perfectly use a simple line to we call it boundary line. Okay, very simple line to differentiate red point and purple point. And this line, okay, this line, of course, this line has for example, if we view it as a new latent space, okay, new latent space, okay, something like that. So this simple line can be described by a very, very simple line, right? This line could be something like that. So we can use the original data, and after we have such kind of rotations, such as shift, such kind of things, this line can easily differentiate these two data points, right? So what is this line means? This line means less softmax. Yeah, exactly this one. Of course, there are some weights right here. So after we have all the information to the last layer, hidden layer, and the output is x prime and y prime. That means these two information has already been twisted, been rotated, been shipped to a new latent space, and this new latent space is x prime and y prime. So that will be x prime and y prime if we use the same terminology right here. And we can use a very simple line, which is represented by softmax. Softmax basically is just a very simple polynomial calculation. Okay, so we can use this line to differentiate purple point and red point. Okay, so that is the this example they use ReLU to do such kind of demonstration. And if you do sigmoid, okay, as we seen before, sigmoid has different squeeze shape, right? So basically that is how sigmoid squeeze those data points. Okay, so basically you can see that I think if you use ReLU in this very simple neural network, okay, I think 20 times of folding is good enough to partition red points and blue points, purple points. But if you use sigmoid, maybe 500 times of folding and twist, okay, that is good enough to partition purple point and red points. So basically, again, activation function is the way you twist, you rotate, you push the data into different latent space. So if you visualize it, okay, it is very similar, but the way they twist is a little bit different. Okay, so let's see. That is the last slide, okay, of our neural network. Okay, so I will talk to you something about learning process. Okay, so here is it. You can see that we have a black line right here. Black line means it is a boundary line. Okay, it's called boundary line, which means how do we partition two different data? Okay, so this example has 300 hidden layers. That means we can fold this original space 300 times, and after 300 times you will get this boundary line, and you map the boundary line back to the original space. Okay, map back to original space in the latent space. That is latent space, right? In the latent space, it is a straight line. But when you map the straight line back to the original space, it would be something like this. It is not a straight line, right? Because you have to do a lot of folding, rotation, something like that. Okay, so if you map it back, you can create a boundary line in the original space. Okay, the boundary line is not a line; it's basically a very strange shape. Okay, so the 4 right here means how many hidden nodes. So I write here. Okay, let's take this one. The soft plus 4 means we have 4 hidden nodes. Okay, so each hidden nodes, okay, because we pass through to sigmoid, right? Sigmoid has an edge. So we have 4 edges right here. That is a little bit difficult to imagine why we have 4 hidden nodes and we have four turning point of the boundary line. Okay, so of course the sigmoid function right here, it has 4 edges as well. However, in this, okay, I say that actually it has 4 edges, but the figure is not good enough for you to observe there are 4 edges. Actually there are 4 edges, but 2 of the edges are very close to each other, so it looks like 3 edges, but actually there's 4. Okay, so I have different let's remove this one to read. I read it here. If you have only one layer of the neural network, so that basically it means you rotate it once, you scratch it once, you squeeze it once by your activation function, and you output, right? If you have 2 layers, you have 2 opportunity to squeeze your data. If you have so that is nodes. So if you have more layers, you have more time to squeeze your data, to transform your data. So here is the notes I write for you. Okay. So basically, if you design a neural network, basically it is similar to folding a paper. That means you trench your data, you squeeze your data. Okay, the activation function you used in your neural network is the different way to fold your data, to push your data from the original space to a new length space. Okay, and the number of hidden nodes you use in each layer, that means how many times of folding in each round. Right? If you have more and more hidden nodes in each layer, that means you can have more folding. Okay, so the next one is the number of hidden layers, is how many rounds of folding. So basically, if you visualize those things, that is just a way to fold a paper, and there are some data points in the paper. And when you fold the paper, you simply just want to differentiate, for example, the red data point and the purple data point. Okay, and if you have more layers, your boundary will be more smooth because you fold many times, right? If you have more neurons, that means for each run you can fold more times. Okay, think about it. Okay, try to think about it. Try to comprehend the mathematic form. Okay, so that A2 W2 A1 W1 X, that is a mathematical form of your neural network, and the right hand side is the network form of your network. Okay, and think about if you visualize your data by using the mathematic form, it is simply just how do you map your original data to a new length space, and in a new length space you can easily do classification, for example. So we make the boundary line in the length space and we map it back to the original space, which creates a very nice smooth boundary line in the original space. So neural network is not that magic. We don't just simply say, okay, I have a very strange weight, and the weight will pass through the information from the left hand side to the right hand side with a magic weight. And the magic weight, something like, okay, 0.3 times your weight plus 0.7 times your height plus 0.5 your hands, your length of your hands equals to your for example your length of your leg. sometimes we may argue that what is the weight stands for? Why it is so strange? What is 0.3 times your weight? What is the semantic definition of 0.3 times your weight? But actually, it does not mean the weight. It means somehow you twist your data from your original space in the new space, and in the new space you can easily do such kind of partition. So you map your boundary line back to the original space, and those weights are how you map your data from the left hand side to the right hand side, to your original space to the lens space, to the lens space. So basically, you don't really need to explain what means 0.3 times your weight, or what is 0.7 times your legs. That's just a way, an optimized way. What kind of optimization? To optimize your loss function. Under optimize your loss function, how did you twist? How did you rotate? How did you push, pull, fold your data from original space to new lens space? And in new lens space, you can easily use a line to partition your data. So you don't have to explain what is 0.3. It is just a way to twist your data to where you have a very low loss function value. Okay, try to think about it. Okay, and I think it is a very important concept to explain neural network, rather than just simply use a figure, okay, like the right hand side figure, to say, okay, we just simply pass the information from the left hand side to the right hand side with the weight. But actually, the weight is very meaningful if you visualize them. Okay, so we have homework today, so maybe you check the tonight or tomorrow morning. I will give you enough time to write your homework, because to help you to practice those concepts. Okay, so that's it. So if you have, make sure you scan the QR code. Make sure you do all the things the university asks you to do so. So okay, that's it. See you next week. Okay.